If you recall in step 18, our goal is to solve and graph rational functions. So now we're going to shift away from solving and get more into the graphing side of things. Before we graph rational functions, we're going to kind of dial it down a little bit to an easier function called a reciprocal function. A reciprocal function is just going to have a number or a constant in the numerator, and it's going to have a expression in the denominator that's going to be linear. And what that means is that x is only going to be to the power 1. We're not going to have any x squareds or x cubes just yet. It's going to stay linear. The parent function, remember we're always talking about parent functions. Last step we were talking about this famous parent function, radical x. And then we also talked about cube root of x. But now we're going to talk about a different parent function, and this one is called a hyperbola or a reciprocal function. Basically, when you graph 1 over x squared, x cannot equal 0, which makes sense because look what happens if I put a 0 in for x. That is not allowed. You may not divide by 0. So for all of these, x cannot equal 0. And we're going to introduce something called an asymptote. You can think of an asymptote as like an invisible line that the graph gets closer and closer and closer to, but never touches. And it kind of looks like it's going to touch it, but it really never touches it, no matter how close we get to it. So when we look at this parent function, the domain, it goes all the way to negative infinity, and it continues to positive infinity, but it is not going to be defined right here where x equals 0, because x cannot equal 0. So when we write the domain using interval notation, it's going to look like this, negative infinity to 0, and 0 to positive infinity. There is an asymptote, like I said, which is the line x equals 0, and then there is also going to be a horizontal asymptote at the line y equals 0. I'll draw that one in as well. And then the graph just fits around these asymptotes. The asymptotes kind of give it shape, if you will. It determines where this blue graph will go. It has two pieces to it, one branch up here and one branch down here. There are no intercepts because it's not going to cross x or y, this parent function. And where is it not defined? Well, like we said, at x equals 0. So let's practice with a couple other examples, finding the asymptotes, the domain, and the range. When we look for the asymptotes, particularly the vertical asymptote, the one that goes up and down, runs up and down, we need to figure out when this function is undefined. So we ask ourselves, when is f of x undefined? And remember, it's going to be undefined when the denominator equals 0. When x minus 3 equals 0. So solving this by adding 3 to both sides, we see that x is undefined at 3. In other words, there's going to be a vertical asymptote at x equals 3. I'll draw it in red. It's an invisible line right here. Here's where x equals 3, and it goes up and down forever. And the graph cannot touch this red line, and it cannot cross it. Okay, let's think about a horizontal asymptote. The horizontal asymptote, notice as if we look at a table of values here, as x approaches goes away from negative, can't even talk today, as x goes away from 3, the numbers get closer and closer and closer to 0, but they never hit 0. Same as we go to the right from 3. They're getting closer and closer and closer to 0, but they never touch 0. So our horizontal asymptote in this case is still y equals 0. Or you might see it written f of x equals 0. Now we need to talk about the domain and the range. I'm going to add just a little bit of space here. I did not leave enough. There we go. All right, looking at a little bit of extra space here. We need to list the domain and the range. The domain is going to come from negative infinity, and then it'll stop at 3, because it can equal 3, and then it's going to pick up at 3 and continue to infinity. The range is going to start at negative infinity and go up until we hit 0, and then it's going to continue at 0 and go on to infinity. Let's try another one together. Over here, we need to think, when is x undefined? And we know that's going to happen when the denominator equals 0. We know that when x plus 2 equals 0, it's undefined. Solving, we see that there's going to be a vertical asymptote when x equals negative 2. Right here. Now I know it looks like that blue line hits negative 2, but it really doesn't. It's an asymptote. So we have a vertical asymptote when x equals negative 2. And it's okay to abbreviate vertical asymptote VA. All right, now starting at negative 2 and going to the left, if we look at this function in a table of values, which we're going to do in a minute, we'll see that the numbers get closer and closer to negative 1, but they never get there. And if we start at negative 2 and go to the right, the numbers get closer and closer to negative 1, but they don't get there. So our horizontal asymptote is going to be y equals negative 1. Now, think back. We're about to talk about some transformations. Notice that our asymptotes, if they had normally started at x equals 0, y equals 0, that point at 0, 0 has shifted down 1 and left 2. The intersection of the asymptotes is now at the point negative 2, negative 1. And notice our asymptote equations. X equals negative 2, y equals negative 1. It's not just a coincidence. Let's talk about the domain and the range as well. The domain goes from negative infinity to positive infinity, but it has a break in it. There's a break at negative 2. That's the one spot that it's undefined. And with our range, we're going from negative infinity to negative 1 to infinity. Like I said, let's talk about some of these transformations. They're going to seem very familiar, just like we did in step 17. When we add a number after the fraction, that's going to make our function go up, translate vertically that many units if we add a number, and it's going to go down if we subtract a number. Similarly, if we have a number in the denominator next to x and we subtract, it's going to go to the right. And if we add a number next to x, it's going to go left. Remember how the horizontal translations are always the opposite of what you'd think they should be? Talking a little bit about shape, if we have a number in the numerator and it's negative or negative before this fraction, it's going to reflect over x. Just like it did when we put a negative before our radical. That made it reflect. Same thing happens. If the number up here is bigger than 1, it's going to be a vertical stretch. And if the number here would be a fraction between 0 and 1, it would be a compression. Looking at this value in the denominator, the b value, if we have a number that's greater than 1, it's going to compress horizontally. And if we have a fractional number between 0 and 1, it's going to stretch horizontally. All right, let's take a look at these numbers. Remember, our parent function is 1 over x. So looking at our function in our first example, what's different? Well, we've added a number outside the fraction. We've subtracted a number next to x. See over here, there's no number next to x. And we've got a coefficient on x as well. So there's 3 transformations happening here. This first one is a vertical shift up 2 units. Next, the number next to x is a -2, which means it's a horizontal shift. Remember, it's the opposite, right 2 units. And then finally, this coefficient next to x is a fraction, which means there would be a horizontal stretch because of that fraction. Now we need to talk about some asymptotes. So again, think how we found the asymptote in the last example. We took the denominator and figured out where it was undefined. When would that equal 0? Well, let's add 2 to both sides. And then we would multiply both sides by 2 to get rid of the fraction. So we have a vertical asymptote at x equals 4. So I'm going to go over to 4, and I'm going to graph a vertical asymptote. Another thing you can do, you can grab your line feature right here. Because I don't know about you, sometimes I like my lines very straight, even if they're dashed. There we go. And then just grab your smallest eraser and make it dashed. It's an asymptote, so we want it to be a dashed red line. It's not part of our graph. It's just an invisible line that we cannot cross. All right, our horizontal asymptote, you guessed it, is going to be y equals 2. So y equals 2 is the horizontal asymptote. So again, we're going to put a dotted line when y equals 2. That's going to help define the shape of our function. At this point, we're going to just use our graphing calculator to find some really nice points to plot and connect to draw our graph. I'm going to use Desmos, have it pulled up here. I've typed the equation into our first space, f of x equals, and the rest of it. And now I'm going to press this gear wheel in the table, and I can see many points popping up. You see these 5 points on the graph. They happen to be the same 5 points that are in the table right now. In my graph that I'm using in OneNote, you can see it really doesn't go much further than about -10 to +10 and so on. So when I pick points, I want to make sure I pick them that'll fit on the graph that I'm using. Let's see if we can minimize and fit both of them on the screen at the same time. Okay, so looking at my table, I have the point 0, 1.5. I like that point a lot, so on my graph I'm going to include that point. 0, 1.5 would be this point. I like the point 2, 1, right 2, up 1. The other points aren't bad. I can graph the point 1, 1 1/3. I just go right 1, up 1 1/3, so a little bit more, and so on. But these aren't going to be enough points. I need a few more points than this. I'd like to get points bigger than x equals 4 so that I can figure out where this graph is going to go from here. So I'm just going to select this and hit enter, and notice I get the point 3, 0. If I hit enter again, gives me the point 4 is undefined, which makes sense. That's an asymptote. We couldn't possibly have a point on the dotted red line. 5, 4. So now I go over 5, up 4. Going to hit enter again. 6, 3 is another very nice point. Hitting enter again. 7, 2 2/3. That's not too terrible to graph. 7, 2 2/3 would be about here. Let's try for one more point. 8, 2 1/2. Over 8, up 2 1/2. So now, if we look at this a little closer, we've got some points so we can kind of tell where this graph is going to go. We just gradually connect them. Remember, we get closer and closer to these asymptotes, but we never cross them. And same right here. Closer to the asymptote, but not crossing. One thing I want to point out, if we go back to our Desmos graph, is to think about those asymptotes. Notice here, it looks like it's getting pretty close to y equals 2, but it never crosses it. It just keeps getting closer and closer and closer, and it never crosses, even though it seems like it might. But because numbers are infinite, it will never cross.